Hello, everyone. Wearable devices collect information that is of personal nature, but they are equipped with little or no security mechanisms. They have a small screen and limited resources. Now, an authentication mechanism is suitable for wearable devices if it is based on the sensors commonly available and also if it is energy efficient. The basic idea is that every person has a unique walking style, and the walking style of a person can be used as a biometric feature. In authentication, the problem is to understand if the current user is the legitimate one or no. So the answer is just yes or no. It's a binary answer, okay? And this is different from identification, where the problem is to identify the user among a set of possible ones. The specific goals of our study are to implement a gate-based authentication system that can be executed on common smartwatches, and also to evaluate the energy required by the authentication procedure when varying the sampling frequency and when computation or part of the computation is offloaded to another device like a smartphone. Here we have an overview of the gate-based authentication procedure. First of all, acceleration is collected at the wrist, and acceleration is then transferred to a walking detection module. The purpose of the walking detection module is to understand if the user is actually walking or not. It's also possible that the user is just moving hands, some spurious movements. And then if the user is actually moving, the data is stored in a buffer and then provided as input to a gate-based authentication module. Here we can see the main steps of the walking detection module. First of all, there is a gate cycle detection phase that is based on recognizing peaks in the acceleration signal. And then a second step is autocorrelation-based filtering. During the first step, the idea is to identify the peaks in the signal. Peaks correspond to steps, okay? And when we have 8 steps, that is a gate segment in our method, okay? When we have a gate segment made of 8 steps, the gate segment is possibly discarded depending on the regularity of the signal, okay? And this is done by means of autocorrelation. So the idea is if the gate segment is not regular enough, just discard it because it cannot be useful for authentication purposes. And then we have the authentication module. In the authentication module, first we have a feature extraction phase and then an anomaly detection phase. The feature extraction phase relies on functions coming from the statistics and signal processing domains. So we used functions like the minimum, maximum, mean crossing rate, average value, median absolute deviation, and so on. And this is done for the 3 components of the acceleration signal and also on the module of the acceleration signal. The output of the feature extraction phase is a feature vector. The feature vector is provided as input to the anomaly detector that is based on a k-nearest neighbor algorithm, okay? This anomaly detection system is a one-class system that is he has a model. It has a model of the legitimate user, okay? And then the possible imposters are recognized as distant points in the feature space. We implemented the method for Android, in particular for WearOS. It is important to notice that this method was originally designed and implemented for microcontroller class devices. So it was a lightweight method since the beginning, okay? We originally developed this method for shimmer devices, okay? Our WearOS implementation relies on a service running in the background for collecting accelerometric data. There is an additional thread for analyzing a gate segment in a separate execution flow, and the communication with the smartphone side takes place using the wearable data layer API to communicate when needed. This code, the Android code, is publicly available on GitHub. You can find the URL on the paper. If you want to use the code, you are welcome. And here we have the metrics that we used for understanding if the authentication procedure is operating correctly or not. First, we have a false rejection rate, that is the fraction of gate segments produced by the legitimate user that are incorrectly rejected. So the real user is wearing the device, but it is incorrectly recognized as an impostor. And the other one is the false match rate, that is an impostor is using the device, but he is incorrectly recognized as the legitimate user. Okay, this is a false match. To have a single performance indicator for the authentication procedure, we use the equal error rate. That is when the false rejection rate is equal to the false match rate. Okay, here we have our experimental setup. It is based on a TicWatch E2 smartwatch. You can see the details on the screen. And then we have a Google Pixel 5 smartphone. Again, you can see the details on the screen. Both are equipped with Bluetooth Low Energy that is used for transmitting the data from the smartwatch to the smartphone. And the energy consumption has been estimated using a battery historian. This is a software tool that relies on execution traces collected by the Android operating system. In particular, we estimated only the energy consumption on the smartwatch side. We are not interested in the consumption of the smartphone, and the reason is that the battery on a smartphone is much larger than the one available on a smartwatch. So we take care only of the energy consumption of the smartwatch side. To have a fair comparison between the possible alternatives that we consider, the evaluation has been done relying on pre-collected traces. So 20 volunteers helped us in collecting gate traces. These traces have been sampled at a frequency of 200 Hertz. And then these traces have been used as an input to the authentication procedure. Okay. So in this way, the data provided as input to the authentication system is going to be always the same. The real accelerometer on the smartwatch was activated to include its energy budget in the results. Okay, but the data was actually coming from the pre-recorded trace. We varied the sampling frequency. The values that we considered are 100, 50, 25, 12.5 Hertz. Acceleration sampling frequency is one of the most important parameters of operation because it has a significant impact on the accuracy and energy consumption. Here we can see the results in terms of number of segments detected and number of segments passing the autocorrelation-based filtering. As you can see, the best results are obtained when using a frequency of 100 Hertz. There is a small penalty when going down to 25 and 50 Hertz. And then there is a quite big drop in terms of performance when going down to 12.5 Hertz. And the same applies also to the number of segments that are regular enough to pass the autocorrelation-based filtering. Here we have the impact on authentication accuracy. As you can see, the authentication accuracy, the equal error rate, remains more or less the same when operating at 25, 50, 100 Hertz. And we have to pay a penalty in terms of performance when going down to 12.5 Hertz. So this basically means that going down to 12.5 Hertz is a bit too much because the accuracy of the system gets significantly worse compared to the other possibilities. And here we have the impact on the battery of the smartwatch. This is the amount of depleted battery in 1 hour of operation. As you can see, when operating at 100 Hertz, the system needs more or less 10% of the battery. This is quite a lot because this is the amount of battery needed in 1 hour of operation. Going down to 50 and 25 Hertz allows us to save a quite significant amount of energy. We can go down to, let's say, 2.5, 4.5 percentage points per hour. It's not so bad. Obviously, going down to 12.5 Hertz provides larger benefits in terms of energy consumption, but we saw that this frequency of operation does not provide results that are good enough in terms of authentication accuracy. And then we have the architecture configurations that we considered. The first one is the completely local architecture. In this case, walking detection and authentication are both executed on the smartwatch. Then we have the partially remote architecture, where walking detection is performed on the smartwatch. And when a walking segment is found, the data is transferred to the smartphone, where the authentication procedure is executed. Then in the completely remote configuration, all the computation, that is walking detection and authentication, is carried out on the smartphone side. So the data is transferred from the smartwatch to the smartphone side where it is processed. And here we have the impact of computation offloading. Okay, we can see that the local configuration is always the best one. Okay, and that in the 25-50 Hertz range, the amount of energy that can be saved compared to the remote configurations, the partially remote or the completely remote configuration, is quite significant. Okay, so there is a quite big difference in terms of depleted battery between the local architecture and the remote ones, the ones that rely on computation offloading. Okay, we can also see that at 100 Hertz, the three configurations needs more or less the same amount of energy. But again, we saw that going up to 100 Hertz is not really needed, because the authentication accuracy is going to be the same. Okay, so the best range of frequency is the one going from 25-50 Hertz. And in this range of frequencies, the local configuration is the best one in terms of energy consumption. Okay, so to conclude, sampling frequency in the 25-50 Hertz range seems to be the right compromise between performance and energy consumption. In particular, I would say that probably the best frequency is 25 for the considered application, because the accuracy remains more or less the same, the accuracy in terms of authentication accuracy, and the energy required is much smaller. And the other conclusion is that computation must be kept local. As we saw, the local configuration performs better than the other one. So there is no need to offload part of the computation. Here we have some concluding remarks. There is nowadays abundant literature on computation offloading, on edge computing, where edge servers are used for running tasks and reducing the computational load of mobile devices. However, our experiments show that for the considered application, the energy spent for transferring the data is larger than the energy saved by reducing the CPU load. And in my opinion, one of the main reasons is that our implementation was based on a lightweight technique since the beginning. Obviously, it is possible that in more CPU demanding applications, offloading can be still useful to reduce the energy costs, but probably it is better to start by designing a technique that can be efficiently executed on wearable devices, provide an efficient implementation, and only after understand if computation offloading can be useful in reducing the energy budget. Thank you.